So you can see how this was made. Now, when designing a synthesis for a polysubstituted aromatic, often a retrosynthesis analysis is helpful. For instance, we know that we can make this from this, okay, by simply putting the bromine here, and that is possible if, since we know that the bromo is by simply putting the nitro group here, we know that this can be done because this is an auto-para director, while this is a meta director. So this will direct it over here. Okay. Now you can see here that the relationship already is a 1,4. So you want to put the weak deactivator first, and then you carry out the Friedrich-Krafts acylation, right? And then you can do the nitration last. Remember, we said that for Friedrich-Krafts acylation, there is no reaction for the Friedrich-Krafts acylation. No reaction for strong and moderate deactivators. Okay. Now, once the ring has only two documents, it should be easier to walk forward. Okay. So you have bromination, and then aluminum bromide. This is bromobenzene, and then you have acyl group there. Then you can put in the nitro group just like what we explained earlier. Now let's talk about nucleophilic aromatic substitution reactions. And as opposed to, contrary to the electrophilic aromatic substitution reactions, the nucleophilic aromatic substitution reactions involve the substitution of a nucleophile by, you substitute a bromine by a nucleophile. The nucleophile here is the OH group. That's the nucleophile here. Or it's the hydroxyl. And the requirement is that you need to have bromine as a leaving group, and also you have to have a strong electron withdrawing group in the para position. Okay. You have a strong electron withdrawing group in the para position. Now, aromatic rings are generally electron rich, which allows them to attack electrophiles. To facilitate attack by an electrophile, the ring must be electron poor, because you can't have two nucleophiles trying to attack each other. The ring must be electron poor, and how you make that happen is by introducing a strong electron withdrawing group. And also there must be a good leaving group, and the leaving group must be in the auto or the para position. And the reason is because the negative charge that forms, or the Mesenheimer complex, is significantly stabilized by the electron withdrawing effect of the nitro group. If you see here, this is the mechanism. You have a nucleophilic attack, and this is upon resonance. The negative charge resides on the carbon that is directly connected to the electron withdrawing group. We learned earlier that negative charges are stabilized by electron withdrawing groups. So that's how we are able to have a negative charge there. Okay. And of course, this can now go backward, and you can have the loss of your leaving group. In the last step of the mechanism, the leaving group is pushed out as the ring re-aromatizes, as you can see here. But don't forget, this is called the Mersenne-Heimer complex. How will the stability of the transition states and intermediate differ from the following molecule? Of course, there will be no reaction. The reason why there will be no reaction is upon attack of the nucleophile. See, upon attack of the nucleophile, you have the negative charge on the carbon, right? And of course, if you delocalize it, you can see that the negative charge is at the para position. The negative charge cannot be stabilized. It cannot be stabilized. By the electron withdrawing effect, by the electron withdrawing group. You can see this, the nitro group is the electron withdrawing group. The negative charge cannot be stabilized that way. Okay. So it's very important that the electron withdrawing group be in either the auto or the para positions. Now the excess hydroxide that is used to drive the reaction forward will deprotonate the phenol. So acid must be used after the nucleophilic aromatic substitution steps are complete. So you have excess sodium hydroxide, and then you have a nitro group here. So if you use an excess of sodium hydroxide after the substitution has taken place, of course it's going to deprotonate the hydroxide and you're going to get the phenoxide. So that's why you need acid to reprotonate. Okay, that's basically what's happening there. So that's for the nucleophilic aromatic substitution reaction. Without the presence of a strong electron withdrawing group, in other words, if you have a mild if you don't have a strong electron withdrawing group present, no reaction occurs. Okay, no reaction, because now you have a nucleophile and this is a weak nucleophile. Okay, but they're both of them are nucleophiles. But in the presence of harsher conditions, interestingly, you have the formation of phenol. The question is, how does this happen? The reaction works even better when stronger nucleophile is used, which of course we know that stronger nucleophiles also act as stronger bases. So if you use the hydroxide or you use the amide, you have the formation of aniline. Okay. Now consider a substitution reaction using toluene. Now, if you use toluene, you can see that the regiochemistry here. That means that the nitro group could add over here, or it could add over here. Now, isotopic labeling can help us elucidate the mechanism. And so upon isotopic labeling, it was observed that there was scrambling between the two carbons. You see? That means that the carbon, this nucleophile will add at either this carbon or this carbon. So you could add at either carbon. See? So the amide acts as a base rather than as a nucleophile. Because you have to abstract this proton, so you have a proton transfer, and you have the formation of this kind of benzene intermediate. Now the nucleophile can add from either side, can add from here, or the nucleophile can add from here. You see? And that's basically what happens. So the benzene intermediate is a short-lived, unstable intermediate. Does the six-membered ring allow for sp to hybridize carbons? No. The carbons are not it doesn't allow for sp hybridized carbon. Rather, this third bond here is actually a result of the sp2 overlap of two sp2 hybridized orbitals. So these are actually sp2. So this doesn't behave as a triple bond. See, this carbon here is still sp2 hybridized, and this is sp2 hybridized. Okay, see sp2 hybridized. And the second molecule of the amide acts as a nucleophile by attacking either side of the triple bond. And that's how it explains, just like what I tried to explain. So either side of the triple bond could be attacked, and so that's why you have scrambling here. Okay, so this can act as a catalyst, yes, because you can see it's generated in the last step. Yes, because it is generated in the last step. Okay. Further evidence for the existence of a benzene intermediate can be seen when benzene is allowed to react with diene via it does other reaction. Of course, you can carry out a trapping experiment. In which the benzene is trapped by furan to give the cycloadduct. Now let's just talk about identify the mechanism of an aromatic substitution reaction. This flowchart can be helpful to identify the proper substitution mechanism. If you have an electrophile, then you have an electrophilic aromatic substitution. If you have a nucleophile, then you have to ask yourself, the benzene, is the benzene acting as a nucleophile or an electrophile? It will act as an electrophile if all the three conditions are met. That means it has a good leaving group, it has an electron withdrawing group in the auto or para position, okay, and it has a nucleophile. So those three conditions are met, then you're going to have what we call a nucleophilic aromatic substitution. But if those conditions are not met, then you're going to have an elimination addition, which goes through the benzene intermediate. Okay, don't forget, for a nucleophilic aromatic substitution to occur, three conditions must be met. First, you need to have a nucleophile. Second, you need to have a leaving group. And third, you need to have an electron withdrawing group in the auto or the para positions.